You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics. We have energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Well, despite the efforts of some passive magnetic component manufacturers, the concept of rated current, it continues to be a point of contention in the power electronics industry. There remains a difference of opinion in how manufacturers should report it and how design engineers can actually use it. Is it an absolute parameter? Are rated current values from different manufacturers directly comparable? The answer to these questions is no. Some manufacturers take advantage of these misconceptions and are deliberately vague about the measurement method used to obtain rated current values to achieve favorable results. The operating temperature of a power inductor is an important parameter for any application. Electrical parameters, such as an inductance and therefore the magnetic saturation, can vary considerably over temperature ranges. The operating temperature of the inductor is an application setting, is defined by self-heating and the ambient temperature. In our equation, T equals T sub A and B plus delta T. T is the operating temperature of the inductor, T sub A and B is the ambient temperature, and delta T is the self-heating of the part. The self-heating is a result of the heat generated by the electrical losses of the inductor. In an SMPS application setting, losses are caused by both DC and AC currents. However, this is highly dependent on the conditions of the SMPS, such as switching frequency and duty cycle. To simplify testing thermal dissipation, the self-heating of parts is measured when considering only DC copper losses. In our equation, P sub DC loss equals I times R sub DC. So where P sub DC loss is the copper losses of the inductor, I is the current of the inductor, and R sub DC is the resistance of the inductor. From this equation, it's clear that parts with higher DC resistance will generate more heat from the same current applied. The heat generated from the copper losses then conducts to the PCB trace through the solder pads and to the core, where it's dissipated through convection and radiation into the surrounding air. When current is applied to the part, the temperature of the part will continue to increase until an equilibrium is reached between heat generation and heat dissipation. The ability of the part to dissipate heat is defined by the thermal resistance of the component. In our next equation, theta sub WA is the winding to ambient thermal resistance. So the winding to ambient thermal resistance equals the self-heating of the part divided by copper losses of the inductor. Although our formula is very simplified and only considers DC current, it still gives important information about how well the part can dissipate heat. More information based on the end application can be found using RedExpert. It's our free online tool that accurately calculates losses and temperature rise for specific SMPS conditions. At this stage, it's important to clarify terminology and principles regarding electrical and thermal parameters. The derivation of thermal parameters evolved in much the same way as those electrical parameters, with similarities in Ohm's law and Newton's law of cooling. For this reason, analogies can be drawn between electrical and thermal parameters. Heat flows through thermally conductive paths as electrical current flows through electrically conductive paths. Therefore, heat generation is usually represented as a current source. Similarly to voltage drop across a conductor, the amount of current that can flow is limited by the conductive or resistive properties of the material, the cross-section it flows through, and the length of the path. This is equally true for temperature differentials between two thermally conductive paths. When considering a simple inductor model, there are two conduction paths of heat, through the winding to the solder pad and through the core to the outer surface of the core. In attached figure 1, we give a visualization of thermal transfer paths in a simplified power inductor. Conduction through the solder pads is divided between the pads. However, what additionally comes into play is the effectiveness of the thermal earth. The lower the ambient temperature is, the greater the temperature differential and the larger the heat flow. For a PCB-mounted inductor, the surface area of the core and the PCB trace size together with its surface area represent the thermal resistances that connect the thermal circuit to thermal ground. Therefore, a full yet simplified thermal model of a power inductor can be defined. This model can be found as figure 2 in this podcast. So where theta sub Ca is the core surface to ambient thermal resistance, theta sub Pt is the solder pad to trace thermal resistance, and theta sub Ta is the trace to ambient thermal resistance. What this thermal equivalent circuit demonstrates is that we essentially have parallel resistors and a number of voltage dividers. If one resistance value changes, the flow of heat will change, therefore resulting in temperatures changing at different parts of the circuit. Consider increasing the size of the part while keeping all other parameters equal. This is going to significantly decrease the core surface to ambient thermal resistance, resulting in more heat flowing from the winding through the core to the ambient air, and less flowing through the solder pad to the trace and ambient air. This is what is typically observed with larger power inductors transferring more heat to the air, whereas the smaller inductors with smaller surface area transfer a greater proportion of heat to the PCB. Now consider increasing the thickness of the winding, meaning lower thermal resistance from the winding to the trace. This will mean a lesser proportion of the heat will flow from the winding to the core surface, with more flowing to the PCB trace. This behavior is typically observed in high current power inductors that use a thicker winding to handle higher currents. Therefore, having a thicker wire both decreases self-heating and increases heat dissipation. Both of these cases facilitate the flow of heat from the winding to the ambient, resulting in a lower self-heating of the part. This means that they can operate at higher currents than smaller inductors that use smaller diameter wire. So how is rated current actually measured? Well, to put it simply, the method involves passing DC current through the part, measuring the hottest part of the inductor, waiting for the temperature to stabilize, and then recording the temperature difference from the ambient temperature. The DC current begins low and steps up with each stabilized temperature raise recorded, resulting in temperature versus current graph. However, the specifics of the measurement technique can greatly affect the result of the measurement. Think about including forced air or convection over the part. This would reduce the core surface to ambient thermal resistance, increasing the amount of heat that can be dissipated. In turn, it increases the rated current of the part. Some manufacturers may not specifically note if any airflow was used, so it leaves room for doubt if the higher rated current values are comparable with values from other manufacturers. Another factor that has an influence on the inductor temperature rise are the PCB trace dimensions. Now, as we've seen with the winding, a greater cross-section area reduces thermal resistance. The same is true of PCB trace dimensions. Those wider traces and increased copper thickness will reduce the solder pad to trace thermal resistance, increasing the flow of conducted heat from the inductor. This also reduces the trace to ambient thermal resistance as the greater surface area of the trace increase heat convection and radiation to the ambient. Again, this information might not be specified in the datasheets, so it leaves room for interpretation by the design engineer. So what does this mean for rated current? Well, as we've seen, rated current values can be manipulated in such a way as to have potentially remarkable thermal characteristics and performance. This also means that the design engineer is selecting parts using incomparable data. This dilemma faced the semiconductor industry some decades ago, where design engineers found it difficult to actually directly compare ICs. For this reason, associations like JEDEC, which is Joint Electron Device Engineering Council, began to standardize measurement procedures and form of thermal performance reporting. What standardization brought was transparency and comparability. Thermal characteristics could not be artificially manipulated to be used as marketing data. However, because of the diverse forms of power inductors, it was actually quite a few years later that a requirement for the standardization of rated current actually came to be. Würth Electronics strives to be transparent with the disclosure of the measurement procedures used and the reporting of rated current data of the temperature rise of power inductors. The method used is based on Section 6 of the IEC 62024-2 2020 standard. The test PCB is contained within a box of roughly 20 centimeters on each side. The test PCB does not contact directly with the surrounding box. Only natural convection occurs, with no forced convection applied to the test PCB. Würth Electronic measurement differs from the standard in that an infrared camera is used in place of a thermocouple. This is done to eliminate measurement error caused by placement of the thermocouple. So in this way, the hottest external area of the magnetic core is measured. Current is then passed through the sample with the temperature allowed to stabilize to less than 1 degree Celsius per minute. Because of the vast range of sizes and construction types with the Würth Electronic portfolio, a number of PCBs have been used, but they primarily follow that of Section 6.3 of the standard. For IEC I subclass A PCBs, the trace width is different dependent on the rated current, but regardless of the PCB used, it needs to be remembered what rated current values on datasheets actually represent. These values are not absolute. They cannot be applied to any application. They are there to give a rough guide as to the current range they can be used in and to serve as a parameter for comparison with other power inductors. The thermal characteristics of a power inductor are influenced by so many factors that it's impossible to characterize the behavior in the final application. So this is where precise knowledge of the measurement technique becomes extremely useful to the design engineer. When all the parameters are known, rated current values cannot be manipulated. This forces manufacturers to be transparent and consistent, avoiding the sham of rated current. In our attached figure 3, the power inductor from the WE LHMI product family is compared with a power inductor of a similar construction but from a competitor. Additionally, an inductor from the WE XHMI series is compared with a comparable competitor's power inductor. Interestingly, in both comparisons, the competitor parts have a higher rated current stated in their datasheets despite having a higher DC resistance than the Würth Electronic parts. The rated current of both inductors were measured and compared using the IEC 62024-2 2020 measurement setup. So for each comparison measurement, the same measurement setup, the same contacting method, and the same type of measurement board were used. The WE LHMI and its competitor on the I subclass C, and the WE XHMI and its competitor on the I subclass D. The temperature of both coils were measured with a thermal imaging camera. DC current was applied to the test boards until at least 65 degrees Celsius was reached, 40 K above ambient 25 degrees Celsius. Despite having a higher rated current value on the datasheet, the competitor 7030 part had a lower heating current of 4.4 amps when compared to the 4.45 amps of the WE LHMI measured on the same I-Class C PCB. We also took a look at the XHMI. Similarly, this product had similar heating current values to the competitor 6060 part, 6.4 amps compared to 6.6 amps when measured on an I subclass D PCB. It should be noted that small deviations in the self-heating curve can be caused by component tolerances, especially in RDC, and can occur even when comparing coils of the same construction originating from the same series from the same manufacturer. So this raises questions about how manufacturers achieved this level of heat dissipation. The use of bus bars, heat sinks, and forced convection can all be used to achieve higher heat dissipation. This should be remembered when comparing rated current values and selecting parts for prototyping. For some power inductors, an additional rated current specified as the performance rated current or IRP might be listed on the datasheet. This is the rated current of the part measured on an I subclass C or an I subclass D PCB. Now, some people might ask or might argue, why use I subclass C or I subclass D PCBs for testing the rated current? But as we discussed earlier, increasing the PCB area and the thickness increases heat dissipation. This leads to higher rated current values. Essentially, the larger trace area and the thicker trace layer is there to replicate the effects of using multi-layer boards, heat sinks, and forced convection, and these are becoming increasingly utilized by electrical engineers. This is especially noticeable in automotive and e-mobility applications. Consider the WE LHMI that has a rated current of 3.4 amps and a performance rated current of 4.45 amps. It's measured on a WE Legacy and I subclass C. Using the part on a 5mm wide trace at the rated current results in a temperature rise of 49 K. This is well within the operating temperature of the part. If the application includes forced convection for reasons of thermal management, the same part on the same PCB at the same current results in a 19.5 K temperature rise. Although this could be desirable in some applications, there is a lot of thermal headroom. When the performance rated current of 4.45 amps was applied to the part on a 5mm wide trace with forced convection, the temperature rise was 34 K. This comparison demonstrates how the performance rated current parameter mimics application conditions that implement thermal management methods. Yes, in this scenario, the inductor could be operated at even higher currents as long as it's below that of the inductance drop permitted by the specific application. It also demonstrates that rated current and performance rated current are numbers to compare and guide in the selection of inductors before prototyping. It should be remembered that there are basic parameters, considering only DC currents with no additional heat generating parts on the PCB. In real conditions, AC losses and the thermal effects of surrounding components would also have to be considered. The actual temperature rises seen in the end applications will vary considerably dependent on the conditions. In conclusion, rated current values found on datasheets serve as a guide for the selection of power inductors, but the temperature rise in power inductors can be influenced by a vast number of factors that are not always reported in datasheets by all manufacturers. It gives a false sense of what the rated current values actually represent. Measuring and comparing similar parts from competitors demonstrates Despite large differences in datasheet rated currents, their performance can be very similar when using the IEC 62024-2 2020 standard to define rated current. Comparing the behavior of a single inductor in different conditions demonstrates how rated current and performance rated current parameters can be used to gauge the performance of an inductor under application conditions. As an early implementer of the IEC 62024-2 2020 standard, Würth Electronic brings new levels of trust and transparency to the rated current values of power inductors, demonstrating no form of manipulation or misinterpretation during measurement or reporting. You're listening to Würth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Electronic technical specialists. We're going to shine a light on topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up podcast.